Some folks call it aluminum, some folks call it aluminium. In my native tongue, we have several words for it, all of them 4 letters long. Hello Internet, my name is Quinn and this is Blondihacks. Working on my locomotive this week, the Pennsylvania A3 switcher, and I'm going to make the cylinder heads. This is a surprisingly important component on a locomotive because not only does it seal the ends of the cylinders, but it's also the start of the support structure for the crosshead and some of the valve gear that's going to be coming soon. So we got to do it right now, so let's go. Next job on the list are the cylinder heads that cover both ends of the cylinders and also provide the support for the crosshead rails that will stick out towards the valve gear. I've got this nice big chunk of brass that should suffice for making all 4 of the cylinder heads, so let's get going. Over to the lathe to, of course, face off the end, as is tradition. Next, I take a random cleanup cut down the diameter to true it up, and that will allow me to take a measurement off of that and calibrate my DRO. With any new piece of stock or new tool like this, you gotta tell the DRO where the tool is. So you create a surface with that tool, measure that diameter, punch that diameter into the DRO, and now you can just start making cuts and the DRO knows exactly where you are. I do have a fair amount of cutting to do, so we'll take some pretty heavy cuts. This being brass, we can do that. And look at the chips fly. This is some content right here. This first diameter is the outermost diameter of the entire cylinder head. All 4 cylinder heads have the same OD. It matches the OD of the cylinder itself, which makes sense. The next diameter down on the front is a registration diameter for decorative covers that go over the cylinder heads. We pretty much have to do the head in this orientation with the stuffing boxes you'll see facing outwards, which is a little bit annoying because that means the critical diameter, the registration diameter on the cylinder bore, is on the inside of the part where it's more difficult to create. That's just something we have to deal with on this part because making it the other way would be impractical, and we have to do it in one setup for concentricity among all of these features. So with that first main shoulder done now, double check that diameter and I can move on to the stuffing box itself, which is also the mounting points for the crosshead rails, as I showed at the top of the show. The stuffing box is the area that seals the piston rod, similar to the steam chests, if you remember those parts. There's a boss with a bore in it that is stuffed full of traditionally something like hemp or graphited yarn. Nowadays we tend to use Teflon cord or Viton O-rings, which are a steam and heat compatible type of O-ring. But the purpose is the same. It allows you to seal a moving shaft against steam and pressure. It's called the stuffing box because it was literally stuffed full of rope. The British are charmingly literal in their namings of railroad things. Next up is some hole features. First, a small hole that goes all the way through the center for the piston rod itself. We can do this with a drill because while it needs to be reasonably accurate, we don't actually want it to be that close of a fit on the piston rod because it risks becoming over-constrained with the piston if we do. And the seal is provided by the rope or the O-rings, so it doesn't have to be that close. Now this next feature is important. This is the counter bore that is going to be the stuffing box itself. So I start with a feeler gauge to get the drill precisely located on the end of the part, and then I'm using a dial indicator on the tailstock to drill to a very accurate depth so I get the counter bore started at just the right depth. And now I can come in with my teeny tiny boring bar and bore that all the way out to dimension. This counter borer needs a flat bottom as well, so we need to do this with a boring bar and not just a drill. This is a very teeny boring bar. It's actually the smallest one I have. I made it just for this locomotive build because there's a bunch of small bores like this. It's a single piece of carbide that's been ground into a tiny boring bar shape. It's a very typical way of making small boring bars. Watchmakers and clock makers do that kind of thing very commonly because when boring bars get this small, you can't use inserts or other more convenient technologies that can be used on larger boring bars. It's got to be ground from a single piece of something, typically high-speed steel or in this case carbide. I worked my way up to dimension with gauge pins, and now we're ready for the next step. We need a shoulder on the back of the part that registers in the cylinder bore, and this is crucial because this is what maintains the concentricity of all of the features on the cylinder head, especially that piston rod bore and the mounting surfaces for those crosshead guides. Now this is problematic because creating a really accurate dimension on the back of the part means that we got to do it with a grooving tool, and it can be tricky to hit an accurate diameter with a grooving tool. The technique that works quite well for me though is to make a series of plunge cuts down an area around where I want the diameter to be, stopping 15 thousandths, something like that, short of the final diameter, and then I can start taking measurements. And when I get down to the bottom of each series of plunge cuts, I always make a sweep across the part as my final finishing cut for this diameter check, and that evens out the surface from all the plunge cuts and also kind of averages out any discontinuities or irregularities in the grind on the end of the grooving tool. That leaves me with a nice consistent diameter that I can take accurate measurements on. Unfortunately, the area is too tight for a micrometer, so I'm having to use my calipers for this. But now I can make final depth cuts the same way, a couple of plunges if necessary, and then once I'm within a couple thousandths of final diameter, then I just make a sweep cut across the bottom. And that is looking really good. That's right on, according to the calipers anyway. Then I can come in with the parting blade and part it off to length. When I'm forced to use the calipers for a critical dimension like that, I just aim for even a little bit outside the high end of the tolerance, and then I can always do a little bit of needle filing if necessary at the end. It's just not worth the risk of undershooting that dimension on something like this, where if I get the diameter wrong, I have to scrap the whole part. And in fact, I did scrap one of these that exact way. I had to make 3, even though I only need 2. And Yahtzee. With those done though, I can move on to the front cylinder heads, which are much simpler because there's no shaft or rod or anything going through them. So I'll start by facing off the end, of course, as is tradition. Now these cylinder heads I'm doing the other way around because I can. I'm going to do the critical dimension on the outboard side of the part so that I can do it with a turning tool, which is much, much easier. But also, as you'll see, there's one more key reason to do a critical diameter on the outside of the part, if at all possible. But first, we got to make some chips to get it down to the OD, as before. Now for that critical bore registration diameter, once again, I'm going to rough it in with some plunge cuts, or facing cuts, if you will. I can get away with doing this in a couple of passes, stopping short of the final diameter on each pass, and then I'll finish up that final diameter with turning. Now the real secret sauce for why you want to do a critical diameter on the outside of your part is because it means you can test fit the part without taking it out of the lathe or without having to part it off and test it on the bench. And that is a huge advantage because you can just go a little bit at a time and you're going to hit that dimension and not risk scrapping the part. However, we do have one more diameter to do on the inside of this. This is once again a registration diameter for the decorative cover, but it's on the inside of the part. Really not that critical, it's just a clearance diameter, so easy peasy grooving. Oh boy, I tried to make something rhyme with grooving tool there, and I don't know, that was chaos. I don't know where I thought that was going. Man, who writes this stuff? You're fired, whoever you are. Oh wait, that's me. Break some edges, and now we have a hole feature to do in this as well. Even though there's no shaft that goes through here, there is a threaded hole for the bolt that secures the decorative cover. Now I'm modifying this part from Kozo's design. He has this as a blind threaded hole for a bolt that goes in from the other side of the part. However, that would require me to turn this part facing the other way, just like I did the back heads. And as I said, that's really difficult because it means you have to do the difficult feature with a grooving tool. So what I'm doing instead is I'm making this threaded hole a through hole, and I'm going to put a stud in here and use a nut to secure the decorative cover. And with the stud silver soldered in, it won't be a leak through the head, and it means I can make this part in a much easier format, as you see here. Yahtzee. Between all of these heads, of course, I'm just facing off the stock and zeroing the Z on my DRO so I know where I am again, and proceeding with the next one. I was able to crank out all 4 heads pretty quickly this way. That's the lathe work done for all 4 heads. Now I need some mill features on them. We've got some bolt circles to do and some other things, so I'm going to need a way to hang on to these. I decided to make a fixture for that. I think it's worth the effort since I've got 4 of these to do, a whole bunch of operations on all 4 of them. Found this scrap of aluminum in the bin. Just had an extra diameter on the end of it that I don't need, so I'll lop that off. There's a pretty good chunk there, so I'll put that back in the bin for something else. The scrap bin, that is, not the trash bin for the British viewers. Now I need a wide, shallow counterbore in this surface. So I think I'm going to try to rough it in with a trepanning operation. I don't have a proper trepanning tool ground for this, but I did find this tool, which has the wrong clearances and also the wrong top rake for aluminum, but I don't know, what could go wrong? Let's ride that lightning. Yeah, that's working just fine. With light cuts and soft materials, you can get away with just about anything. Doesn't mean you should, but you can. For a very wide, shallow bore like this, trepanning seems like a nice way to rough it in because it's too shallow to start with big drills, and it's so wide that doing it entirely with a boring bar would take forever. So this will get me in the ballpark, and then I can bore it to final dimension. Because of the angles on that tool, I stopped well short of my dimension, then squared it up with the boring bar first, and then I can start taking measurements to see where I'm at. Measuring this is a bit tricky because the bore is too shallow for my snap gauges, so that's a bit inconvenient. So I am going to have to use the guessimeters once again to measure this. Now, this is not very accurate for small diameter bores especially. Calipers are pretty poor at this, but it'll tell me when I'm reasonably close, and then I can just start taking light cuts and test fitting until I'm there. I'm aiming for a very close fit on the cylinder heads, and that is money. That is very, very good. I almost can't push that in or get it out again, which is perfect for a fixture. And I'm also going to put a threaded hole down the center of this to help with securing the heads in place. You'll also note I turned an OD in that same setup to give me a concentric reference, which might make setup easier. Over to the mill, I'm going to hold this in a V-block, and I'm going to dial it in centered up on the spindle of the mill. There's lots of ways to do this. I'm going to use my coaxial indicator for this, which is sort of like a video game. You have to just move the hand wheels a little bit at a time until the needle stops moving, kind of closing in on zero motion. I don't know if it's the quickest or the most accurate way to do this, but it's definitely the most fun. So there. Okay, we are ready to go with the first part. I'm going to start with the bolt circles around the outsides of the cylinder heads. I'll bolt down the first of the rear heads. All 4 heads have the same 6-bolt pattern all the way around them, so that makes it easy. That's why I wanted to do a fixture for this, because this setup will then repeat, because I got a lot of bolt circling to do, and all 4 of them are the same, so if I can make a nice repeatable fixture, that'll save me a lot of setup time. I center drill each of those positions and then drill them through. These are just clearance holes for the bolts that will mount the cylinder heads to the cylinders. Now, because this fixture repeats so nicely, I can pop that one out and pop the next one in, and I don't have to find center again. I don't have to reprogram the bolt circle feature in the DRO or anything like that. I just pop in the next cylinder head and I'm ready to go. I can run through all 4 of them very quickly this way. The front ones are a little trickier though, because I can't fixture them the same way. That center hole is threaded and too small to be used for that. So instead what I'm going to do is center drill and drill the first of the bolt circle holes, just using my finger to kind of hold it in place. My fingers are just keeping the part from rotating, from spinning in the fixture. The fixture is close fitting enough that it's holding the part securely. It just might tend to spin. Then once I've got a single hole drilled, then I drilled and tapped that same position in the fixture, and that gives me a second point now, or I guess a first point for these heads to secure it. And really all this bolt is doing is keeping the head from spinning while I do this. The very close-fitting fixture is doing the rest of the holding. This is easy and safe to do because this is just brass and these are very small holes. Tool pressure is extremely low. The drill isn't going to grab the part or do anything crazy like that. So you can just hold the part with your fingers in a situation like that, along with the help of the close-fitting fixture. The other front head was done the same way, of course. Then it's on to the cylinders. I've got to bring those back in to do the bolt circle on those as well. So I'm going to set those up thusly, referencing the port face on the fixed jaw of the vise, and once again using the coaxial indicator to dial in the bore and do the same bolt pattern as before. The orientation of this, of course, is critical because all of these bolts have to miss all of the internal features of the cylinders. There's steam passages and drain holes and such everywhere inside this part that we have to miss. Fortunately, Kozo makes that really easy. The bolt circle lines up at 0 degrees with the port face. I've made a bunch of steam engines, and some of them make this very hard. Sometimes the bolt circle has to be at 11.5 degrees in order to avoid drilling into a steam passage. And I have done that, and honestly, if it happens to you, it's not the end of the world. Just put some Loctite 545 on the bolt that broke into the steam passage to keep it from being a steam leak, and it's honestly fine. With an end stop, that setup repeated for the same end of both cylinders, but then for the other end of the two cylinders, I had to use a mirrored setup with the end stop on the other side, and I had to find the bore again, but not a huge deal. All right, here we are with the cylinders all prepared. We can now bolt the cylinder heads in place. We're going to be using the cylinders as a fixture for the next set of operations on the rear heads. I need to make a couple of flat spots that are the mounting positions for the crosshead guide rails, and they need to be very well aligned to the features of the cylinder itself. So using the cylinder as the holding fixture for this cut makes a lot of sense. This is suggested in the drawings, and I can see why. So by making this cut in this position, we guarantee that the flat surfaces will be parallel to the port face, which is important here. These get drilled and tapped, but not all the way through. These are very close to the stuffing box bore, but not all the way through. And those are for the mounting bolts themselves that are going to hold the rails in place. Now, conveniently, these cylinders are self-indexing because they have very square reference surfaces on them. So I can flip that around, clamp it in place 180 degrees, make the same cut on the other side. And we're going to have nice parallel surfaces to mount the rails to. The distance between these rails is very, very important. I'm aiming for 788 on this dimension. I was very careful to try and hit that. Let's see how we did. That'll do, pig. That'll do. One last feature on the side of the stuffing box is a threaded hole for a set screw that clamps the gland nut in place. Once again, these cylinders are very conveniently self-indexing at 90-degree intervals. Next up, I called an audible and went back to the cylinder heads, and I decided to put jacking screw threads in them. I also did this to the steam chest covers. If you've taken apart any heavy equipment, especially like farm machinery, you'll find jacking screw threads on features that are clamped together, like flanges, bearing collars, that kind of thing. What it allows you to do is when you need to pull those pieces apart later, you can thread a bolt into that thread, and when you crank it down, it acts as a jack to separate the two pieces, hence jacking screw thread. On heavy equipment that operates in harsh environments for long periods of time, those flanges and related components can get so seized together that you'll never get them apart without the help of a jacking screw. This shouldn't be a huge issue for me because I was planning to use paper gaskets for everything here. However, I might end up using Loctite 518, which is actually what's suggested in the drawings. Now, this is not RTV, if that's what you're usually thinking of when you think of gasket maker and sealants for flanges. Loctite 518 is more like a very thin glue for sealing well-machined surfaces together. It just prevents capillary action and similar forces from causing leaks between two very well-machined surfaces that don't really need a full gasket. And the nice thing is it doesn't add a bunch of thickness to the area, which might mess up tolerances or other important dimensions on the assembly. You'll see this stuff used in situations like split-case motorcycle transmissions where they don't want a full gasket between the halves, but you want some kind of insurance against leaks there. I haven't yet decided where all I'm going to use gaskets versus the Loctite, but anywhere that I do use the Loctite without a jacking screw thread, I will be having a very bad day if I ever need to separate these parts, which I will need to do. Steam engines always need taking apart to adjust valve timing and so on. I can finish up the front heads now. I need to put those studs in that I talked about. This is my modification to these parts. I cut the ends off of some screws for the studs themselves, and now I'm going to silver solder them in place so that they aren't steam leaks. In addition to making manufacture of these parts about 50 times easier, I think studs are honestly kind of nicer in this application. Feels more like how the prototype would have done it. They tend to use studs everywhere because it helps align heavy components when you're assembling them. I don't see any reason that this needed to be a bolt the way Kozo had done it, so I'll make my own decorative acorn nut or something to attach the decorative covers when we get there. A little bit of cleanup, and those are the two front cylinder heads now with their studs soldered in place. I'm confident those won't be leaks, and those are going to bolt on in place just like that. Speaking of which, let's get everything bolted in place now and see how it all fits together. I think I'll probably end up using the 518 sealant on the cylinder heads and the steam chest bodies, because those are components that don't need to come apart really all that often, and particularly on the crosshead guide rails, I don't want to mess up any fits or tolerances there. However, on the steam chest covers, I'm almost certainly going to use a gasket there, because steam chest covers have to come off all the time for tweaking valve timing. There we go, that's starting to look like a boat now. We've got some cylinders pretty much complete. All that's left is the decorative cover pieces that go over a lot of this stuff, which we will get to in a future video. But so far, I'm pretty pleased with how those are looking. If any of those bolt heads were going to be visible in the final product, I would probably replace them with studs and nuts because that looks more prototypical. They're always going to be studs and nuts on the real thing, not giant slot-headed screws, but it's all going to be covered, so it's all good. I hope you enjoyed watching this process. Thank you very much for watching. Thanks especially to my patrons for making all of this content happen, and I will see you next time.